The name of my lecture connected with graphene-based materials, the nanomesh and superlattices and structures and properties. I am designer of nanostructures. That's the main goal of my talk. To see you some new structures and how can these structures will be estimated by quantum mechanical different chemical methods, and my asking to chemical computing workers about this. I don't know why. Нижний? Okay. Two couple words about graphene. Graphene is the simple two-dimensional materials, one layer in one atom's thick. The first paper about the theoretical estimation electronic properties, this Wallace, and he use only simple description, looks like tight binding method, and you can see the unusual picture of energy dependence from wave vector. These peculiarities of spectra connect with the structure, the structure of hexagonal net of carbon in this picture. You can see we have two sublattices, red and green, and that's why this sublattice include to the structure dependently, and that is why we obtained that binding calculation picture. Now many people check the structure by more accurate methods, and all of them obtained the same picture, because this structure did not destroyed under environment. And when graphene, when we cut graphene on the as length, you can see here the simple nano ribbon length, and with white. It can be obtained a different kind of electronic properties. These ribbons, for example, simple when ribbons zigzag edges, we obtained semi-metal behavior, and when we have armchair edges, and the spectral electron spectra depends on width or how when when we change whites and change the electron vector in this direction, and these electrons move through this ribbon as electron in waveguides. That's why we cut the picture of two-dimensional graphene on the some place perpendicular to the x, y wave vector. And that's why when this place connected with quantization of electron through this direction, through the whites, and we can obtain crossing your plane direct points or not crossing direct points. That's why many interesting things connected with this nanoribbons. And here we see the simple rules for armchair graphene nanoribbon. And this is picture of tight binding calculation, and this picture DFT calculation. And you can see the very close behavior of energy gaps these ribbons. For example, when we have 3p plus 2, we obtained semi-metallic behavior when we check tight binding, and similar semi-metallic with very sharp gaps for armchair nanoribbons. And this is some simple explanation of this behavior, and now it's very interesting to prepare some graphene structures which have opening of gaps. It's possible to these materials when we prepare looks like mesh when we organize some holes in graphene, looks like here, and various techniques have been developed to produce such graphene nanomesh, and this is first experiments about nanomesh, and but it's need to understand the behavior of such materials. The first prediction of such materials was prepared by this group in this paper, and they considered triangle antidot lattice, looks like here, and classified these holes, and these holes with zigzag edge, these holes with anti armchair edges, and when we change the parameter the width of this hexagon and radius and radius on holes, we can obtain different kind of gap, energy gap, these materials. And I didn't have possibility to to ask you many words about that, but I also see you some preparation. This holes looks like here. You can see chemical engine, when we use chemical engine and influence of some chemical solution destroyed graphene and organize looks like this hexagonal holes. And in this paper, they prepared different kind of nanomesh. Now the width of the width nanoribbon between holes has about 7 nanometer, and that's why it's a need to check this materials theoretically, but it's need to use many atoms up to 1,000 atoms. That is why it's not simple to check theoretically these materials. And the second problem of this mesh, and we can we obtain distribution of the original this nanoribbons between holes. And this is problem for experimentalists. Another possible to prepare it using some organic molecule put on the surface, carbon surface, and then exit washing moves this moves to the nanomesh, prepared nanomesh graphene. It can be, it must be used also porous magnesium oxide layer or aluminum oxide materials, porous, nanoporous materials, and so on. And that's why continuous semiconductor nanomesh film can be used for fabrication integral devices and circuits, and there are many theoretical papers connected with this nanomesh, and this is pathway toward practical application graphene as semiconductor material for future electronics and so on application. And we decide to check this to check the nanomesh materials and compare nanomesh properties when with the graphene which has different type of defects. Looks like here you can see adsorbed hydrogen atoms, and when we have periodical structure, looks like here with sp3 atoms, carbon atoms in this area, you can see we observed behavior looks like here. It's the same very simple behavior, and then when we change the distance between defect areas in this direction, we change electronic properties. When we change this direction, we cannot change these electronic properties. And that's why connected with the how can graphene spectra divided by periodic structure, periodic structure structures, and we obtain this similar semiconductor very close, the similar semiconductor rules for rectangular two periodic superlattices, and they check different kind of area, defect area. For example, as I see earlier, when we have hydrogen adsorption, this behavior. When we have fluorium, we have red area, and when we put boron N, we change this area graphene into boron N. The same behavior, and the same behavior as we use graphene nanomesh. That's why this is why the common rules for two-dimensional periodic structure with two-dimensional periodicity of defects. This fact is very important from an experimental point of view, because process of passivation graphene surface by fluorine atoms and nanohole preparing are preferred for experiments. Similar results now obtained in this paper for graphene nanomesh. And it's interesting to use not one layer, but two layers. And it's my dream was earlier to prepare some some nanotubes connections, nanotubes connections and nanotube structures looks like here. And now I suppose we have possibility to prepare such structures. At first we consider the B-layer graphene, for example, AA stacking B-layer graphene. You can see the usual picture of AA stacking B-layer. This is two layers of graphene connected by van der Waals forces. And when we cutting the special preparation, we can obtain a different kind of rectangular hexagonal nanostructure, nanotube mesh, where nanotube connected between the graphene parts, B-layer graphene, or connected nanotube one to another. And we can I can put experimental results prepared in these papers, and they obtained in high electron resolution microscope the constructed border of two-dimensional layer of graphene, and these H atoms connect one atoms of upper layer connected with atoms of bottom layer and construct looks like semi nanotubes. You can see in these models, and that is why it can be proposed zipper mechanism of this connection. Looks like here. At first one atom, and then some atoms connect on this direction of edges. Looks like here, and construct looks like structure in this picture. It's possible when we use electronic beam and cutting graphene, looks like here on this direction and this direction, and after producing these holes, we obtained the picture looks like here too, but because we have very high chemical active atoms on the border, and this border connected and transformed to the nanotubes graphene B-layer structure looks like here. We check these structures, but unfortunately we have not possibility to check many atoms structures. This structure connect about only 500 atoms, and here you can see the picture of cutting nanoribbons by electron beams, looks like here. And after that, we check by using molecular dynamic calculation how connect this the border of B layer ribbons, and our calculations show that we have a very small barrier between first step when when connected only one pair, and up to 4 steps when we connect 4 atoms, and after that we observed the zipper mechanism on connection on along the border of nanoribbons. That is why it proposed for us to construct different kind of structures. Looks like one quasi one-dimensional structures, all sp2 structures, and with closed borders. Looks like here. You can see this nanotube. This is B layer nanoribbon, and we check electronic band structure and observed semiconductor behavior this structure. That's why when we use electron beams preparation, we can construct not only two-dimensional and three-dimensional structures. Oh no! Two and three-dimensional structures. For example, we also check hexagonal structures. Looks like here, and this electronic properties depends of two main parameters: size hole and distance between holes also, and obtain different behavior of energy gap in this paper. When we change the distance between holes, we go from semiconductor to metal behavior, and when we check the distance between when we change the distance of nanotubes, looks like here, we can change different behavior of electronic properties. That's my dream. When we use electronic beams, we can construct different kind of electronic elements. Looks like here. For example, a ring with two carbon nanotube terminal, ring with one carbon. This is different kind of electronic elements, and which I suppose will be used in the future, maybe not so earlier, but it's possible. This all construction is very stable. Some application, this, for example, we can use, for example, 6 terminal nanotube elements, and elements more complicated, and these elements can be used for some elements of computer, nanocomputer. And then when we put voltage from this or that electron voltage in this structure, we can use this element as electronic nanoemitter. And the conductive nanomesh without carbon, without chemical activity carbons will be used as good elastic and hard graphene sheet for different application. That's why thank you for your attention. That's my colleagues which work with me. Thank you.
Thank you very much. A couple of quick questions.
Yes. Thank you for the presentation. And I have a question about band gap. That you showed a picture where you have this band gap depending on what material you put in the graphene.
Mm-hmm.
But maybe I didn't hear. What package, with what method you use for calculating band gap? Because we all know that DFT underestimates band gaps and Hartree overestimates them.
Yeah.
What kind of package did you use when you calculate these band gaps?
You can see here, yeah? We check this, we consider very simple pictures of two-dimensional. And this calculation, we use DFT method. And check also the simple tight binding DFT plus. And we obtain the same results.